Well, good morning. For me, this is an interesting opportunity because, in general, I am not a high-performance computing guy, I guess you would say. I use a lot of the systems day to day, but seeing the companies that I say, oh yeah, I run on the SGI machine or the Lenovo machine or whatever that is. It's a different place than I would normally present. So this is interesting, and in a lot of ways, this is sort of a thank you from my perspective for allowing me to do the work that I enjoy and providing new and interesting ways for me to advance some of our work. For me, as Paul mentioned, I've been involved in New York, Louisiana, Texas, most of the Gulf states, doing hurricane storm surge modeling, the validation of these models, the development of the actual code that runs these models, and it's all occurs in a high-performance computing environment. And a lot of this stuff has evolved very heavily over the last 10 years thanks to some of the advancements, and that's what I want to bring to light is sort of how that helps some of the planning that goes into a lot of these different studies. The ability to do more faster has tremendous effects, and I want to show some of the actual implications of that. Before I get started, I have the necessary sponsor slide. We are funded for most of our work through Louisiana, through CPRA, which is the Coastal Protection and Restoration Authority of Louisiana, and the Water Institute of the Gulf. Both of these members are extremely proactive in promoting many different types of high-performance computing and putting lots of investment for their scale. It's a large investment for them, and they've done a lot for us. And also University of Notre Dame, who supports a lot of our high-performance computing, ERDIC with the Army Corps of Engineers. And of course, thank everyone here, and of course Paul for inviting me. It's very nice to get a reach out from him, and this is only 10 minutes down the road from where I live, so this is an easy travel day for me. So some of the motivation for the work that's going on in Louisiana, here's some stats. If you're not familiar with Louisiana, they are having a tremendous land loss crisis. They've lost 4,800 square kilometers of land since 1930, and most of the models currently predict an additional 4,500 square kilometers of land loss. That's due to lots of factors. There's a tremendous subsidence in the area. It's a very, very high subsidence area. Of course, these storms hit and they completely destroy islands. There was a National Geographic piece recently about Pelican Island. Pelican Island is almost, I'm sorry, not Pelican Island, Cat Island in Louisiana. It's almost completely gone, and it's one of the very few pelican habitats left in the United States. And pelicans are very, very specific about where they will breed. And it's a project that CPRA is taking very seriously, and they need to restore it quickly. And of course, the economic effect is tremendous. If you look at the way these storms hit the Louisiana coast, due to land loss only, there's an expected additional $23 billion of damage due to storm surge. That's not total damage, that's additional damage. And so these are some incredible numbers just in Louisiana. And so it's been a motivation for a lot of work that has to go on. So just run through of what I'd like to do. I'd like to give a quick background on the numerical models that we use for some of these studies and take you through the years and how we've done these to date and what we've been able to achieve as we are able to do these plans every 5 years, the additional detail that we're able to get because the high-performance computing is advancing in such a way that we can do more in a timeline. So the numerical model that it uses is called AdCirc. It's a circulation model. It's a finite element-based circulation model. It solves the shallow water equations. It has a number of different formulations, which no real need to get into, but it uses MPI, message passing, or serial, if you so desire. And that's coupled with a wave model called SWAN, which solves the action density equation for non-stationary waves, although it can also look at stationary waves. And this can be on many different types of meshes in serial, OpenMP, or MPI. And a fairly standard METIS decomposition. So this is what our domain looks like for the Louisiana hurricane storm surge model. So we model everything all the way out into the Atlantic in order to get some good tidal conditions for us. And we concentrate our resolution in here. You can see these black lines show where our local processor boundaries are. And obviously there's much more concentration of effort in the Louisiana area. And then the way this works is AdCirc runs on the finite element mesh and communicates with SWAN. The nice thing about using a setup like this is AdCirc is much more picky about its finite element mesh. So if you have a good AdCirc mesh, in general, you'll have a pretty good SWAN mesh. And they communicate locally, which is fairly easy stuff. It's just a couple subroutine calls to get them to talk to each other. And then they also communicate along the boundaries of the processors and exchange some information. So the two models exchange information across memory, and then the processors themselves exchange information. And the way we would do this in real time is we would take AdCirc and we would start the simulation. And I've sort of denoted it as these small little lines. AdCirc takes very small Courant limited time steps. And we'll run it for 10 minutes. And then we'll take information about water levels, currents, wind information, and we'll pass it to SWAN. And then SWAN will take one large 10-minute time step, which is generally adequate for waves and waves, how they evolve. And then we'll pass that information back to AdCirc, which it'll then use for the next 600 seconds. And sort of the background of some of this works from a communications perspective is we have cores. And generally, for most of the models, they'll run between 250 and 2,500 cores. And so you have cores 0 through n up here on the screen, and they'll be doing simulation. And when we get to a defined output interval, they'll send their information back to core 0, and core 0 will write. And of course, this weighting is a fairly, I guess, poor setup. And so what we've done recently is we've dedicated processors to the task of writing. So if we break off two processors out of that chunk, what we'll do is we'll have writer 0 and writer 1, and we won't let them participate in the simulation. And then our weights will all be on them. So we'll simulate. Cores 0 through n will send the output information to writer 0 and 1, and they will write this information to the disk while the rest of the processors are able to continue with the simulation. This is something that had to come about because high performance computing had allowed us to make these models so big that we couldn't write the information to the disk fast enough in a reasonable way. And so we had to start evolving the model a little bit. So here's just colored by finite element mesh size, some of our Louisiana domain. And so as we zoom in a little bit, we can start to see how these things are set up. We have channels and very critical features in the more red colors, where we're trying to resolve very accurately the fluid flows. As we zoom in on the west of the state, you can see even some more channels that run horizontally through the state. And when you do this correctly, we can generally get a pretty nice model validation. Our validations are generally on the order of the error of the measurement itself. which is sort of what we aim for. Our validation graphs generally look pretty good. So if when we take all this huge amounts of data and no small number of error sources, we actually are able to do fairly well with our simulations. And so when we take all this and we have a model that reproduces history very well, what we can do is we can then look at defining statistical risk. And the first time this had been by FEMA in 2007 and the subsequent LACPR study. And what was set up during that time was a suite of 446 synthetic hurricanes to sort of fill out a stochastic analysis. And all these storms were run on all these various tracks. And so you can see these tracks that are shown up here. Not only are there these tracks, but there are also different hurricane parameters on each of these tracks, different forward speeds, different wind speeds, many different iterations on the same storm to start to fill out what your envelope is. And then what was done in the LACPR was a limited number of analysis of future projects that were proposed, people were thinking of implementing in the area, that they want to see what's the effect on the statistical returns for these projects. Is it feasible to build? Does it affect other people in ways that are negative? If we build a levee here, does it flood my neighbor in a way that he wouldn't have been flooded previously? And how can we solve that? And one of the issues is when you have these suites of 446 storms and you're using about 512 processors for 10 hours at a time for each one of those storms, it begins to become very difficult for some of the smaller, HPC users to get that sort of CPU time. It's very significant, and because of that, there's a very limited number of projects you can analyze. And so you almost have to pare it down to one or two projects before you've even started your analysis using the models. And that's, in a lot of ways, a problem, because you can't see how other models or how other projects would perform that you didn't already know how they were going to perform. So then in 2012, we ran into a situation where we wanted to look at lots of different landscape changes. We want to look at different sea level rise scenarios, and we want to look at them at different times 50 years into the future. So 10, 25, 50 years. And even with one or two projects, that's a fairly significant lift, especially compared to what was done in 2007. And then we also add into kind of the fold, how do these projects affect each other? So we can see how these projects work on their own, but does one project gain benefit from also being built with another project? And so you can see each level of complexity adds to the number of simulations that you want to do. To complicate things more, the 2012 master plan also had models for vegetation, water quality, ecology and hydrology, wetland morphology, barrier island morphology, fish and wildlife, of course storm surge and waves, and finally a damage and risk assessment model. And these were all very closely tied together in a way that the output would be fed into the storm surge model and finally to the risk model. So if you look on the screen here, you can see there's the eco-hydro model as number one, and that feeds a stage into both the wetland morphology model and the barrier shoreline morphology model, which feeds into the wetland morphology model, which feeds into the vegetation model, but the vegetation model also feeds back into the wetland morphology model. And each one of these, we would look at whether different sea level rises that are possible. We don't want to just assume the NOAA high curve We would like also look at a medium curve. What's something even higher than the NOAA high curve? What would happen if there's a drought conditions and we have some die-off of certain types of vegetation? Would that vegetation allow more storm surge to propagate inland? And so all that information is then fed into the storm surge and wave model through topographic and bathymetric information, as well as land use, land class information. And we get to a point where we need to analyze all these scenarios, and we need to maintain some sort of acceptable level of accuracy. We truly cannot do 446 storms for each one of these scenarios. But by running 446 storms, we can then pick out what storms are most critical to defining our risk. And we can take those storms, in this case it was 40 storms, and look at the 34 hurricane protection projects that we wanted to look at and group them into 7 non-interacting groups. So you can see here, this is one of the groups that was used in the 2012 master plan. These projects are sufficiently spaced that the induced surge by any of these levees would not affect the outcome of another levee. And what that does is it allows us to define a benefit for each individual project. And here's an example of the results. So on the left, you can see there's the storm surge for this simulation without any projects in place. And on the right side, with these projects in place. And then in the middle bottom, you have the difference. And so depending on what sort of assets are behind each one of these levees, we can start to look at what's the damage reduction associated with each one of these. From there, we'd want to look at how these projects interact with each other. So if we implement all of these projects into all of the different ecology, water quality, et cetera, models, how could this suite of projects that we've defined as the most beneficial interact together to create the least damage? And so what you'll see here is this is one of the scenarios that was determined for Louisiana's master plan. There was a suite of projects that was defined. You can see there are some areas where there's not a levee, such as, right at the coast on the west of the Bird's Foot, there were some barrier island changes that had occurred. They were planning to do some barrier island restoration, and so there was a slight reduction in surge. And all of these sort of feed in together, so we get all these scenarios, all these groupings, these different time levels, and we tackled approximately 1,640 simulations in 2012 to the tune of about 6 million CPU hours, which is something that the state of Louisiana themselves had not funded ever previously to this effect. And seeing these benefits, they've decided that, yes, high performance computing and storm surge modeling is something that we're going to need moving into the future. And so as recently as last night, this has begun. The first simulations are chugging as we speak here and hopefully not going unstable. We've increased our effort for the 2017 master plan. So we'd like to do 60 storms for our screening at 3 time levels for 3 different sea level rise scenarios. And then moving forward for the master plan analysis itself, where we take this suite of projects and put them together, we'd like to do 154 storms for 3 scenarios. And that amounts to, right now we're planned for 7,700 simulations. My gut says that the scope will creep and we will look at probably more 8,500 to 9,000 simulations, which if you start to think of it just from a QA, QC perspective, not a high performance computing perspective, we're looking at on the order of 750,000 human reviewed plots, which is no small task, and I probably will be blind by the end of this. But we're looking at somewhere in the area of 10 to 12 million CPU hours. And so to take you through what we've used over this time, 2007, we used Army Corps Sapphire. 2012, we purchased a machine that worked very, very well at the time with about 1,000 cores. That was a dedicated resource to Louisiana's master plan. And just as recently as maybe 3 weeks ago, we took delivery of a new Lenovo machine with about 1,500 cores. Again, this is a dedicated resource just to Louisiana's master plan. It's not planned to be used for anything else in the state. And so what I've done is I've plotted up some of our scaling curves just to see how things have increased over time for our AdCirc model, and we're seeing essentially pound for pound, a 2x speed up just in AdCirc model performance just by upgrading to the new machine. So this has been a really, really nice feature for us to be able to do more and more simulations and define more and more scenarios for the policymakers who want to make these decisions. Because what happens is, if you look at how all of these simulations come together and ultimately define some sort of risk, the more detail you can have to make an informed decision is extremely important. So if we can only look at 50 years into the future, we're not entirely sure when is the optimal time to have a project on the ground. If a project can make a difference at 50 years in the future, that's great. But if it's not going to really have its full effect until, say, 35 or 40 years into the future, maybe it doesn't need to be built for another 20 years. Maybe there's something better that we can spend our money on that would have an effect right away. And so being able to look at these at different time levels is extremely valuable. Finally, and this is sort of something that's interesting to me and maybe some people who live along the Gulf states, because of the speed up of these models and the computers, we're able to add detail to the forecast simulations that can be done. And there's a group right now that we're lucky enough to partner with that runs hurricane storm surge forecasts in real time using high performance computing assets as soon as National Weather Service puts out new forecasts. So if you go to the website coastalemergency.org, they will provide a forecast and a track and help define risk for individual areas. And this is such an improvement over what has been done previously, where you would run essentially a desktop model because these high detail models were not fast enough. And so this is something that's evolving. It's obviously not an official product yet, but the hope is that as computers progress, we can get forecasts with these high level of details that aren't tuned models that need to be calibrated for each single run. We can just use basic physics to define hurricane storm surge risk. And that's, so thank you very much.
Some questions for Zach? Yes, sir.
Michael Wachowski, Raytheon. Are you working with NOAA's National Water Center?
We're not working with them specifically, but we do have some colleagues at NOAA. I believe Jesse Fine is one of the guys at NOAA that we work with, but we don't have any projects with them specifically at right now.
I asked simply because at the AMS meeting about a month ago, they did some presentations and they are trying to update their flood models quite a bit and get a much larger degree of resolution using modeling and other empirical data, and it seems like it may fit very well or help augment what you're doing. That's all.
Thank you.
Any other questions? Yes, sir.
Thank you. I was curious, working with AdCirc and SWAN, do you get all you need from the current development roadmap, or do you actually take the source and make changes yourself?
It's a little bit of both. I serve as part of the development team on AdCirc, and so I have my hands in the code a lot more than most people would, but in general, when we run these sorts of production models, we try and use release versions, unless there's a feature that's in the pipeline that's critical that we'd like to use.
And just a follow-on question, you showed the improvement from 2010 to 2015, which you attributed to hardware, but I would expect there was some optimization in the software as well during that period.
Very little, honestly. There may have been some optimizations that weren't totally flushed out at Notre Dame where we run these simulations, but it seems to me that the hardware is mostly to blame because we've run these simulations. Those simulations were all run at the same time with the same model, with the same mesh about 3 weeks ago.
Any other questions? Okay, Zach, thank you very much.
Thank you.